Hello, welcome back to the NPTEL online certification course on deep learning. Since our previous class, we are discussing about the normalization, and in the last class we have discussed that what is the role of normalization, what we need normalization techniques so that your classifier design can be faster or the training of the classifier can be faster and the classifier can be more stable. Particularly, we have taken an example with the help of batch normalization techniques, or why you are going for batch normalization is the classifier training is or the learning process is in the form of batches. So the algorithm which is mostly used is what is known as batch gradient descent or batch stochastic gradient descent approach. So where for training of the classifier or training of the deep neural network, you feed your training data into mini batches where every batch contains maybe say 10 training examples, 15 training examples, 100 training examples and so on. That depends upon whether your batch size will be small or batch size is large. Okay. So we are assuming that we are given these two different batches, and the problem that we want to address, or the classifier classifies the flowers category from non-flower category. So when you give the batches, every batch will contain some images from the flower, some images from non-flower. So these are the two different cases that have been shown here. On the left hand side we have batch 1 and on the right hand side we have batch 2. So you find that the images of the flowers which are in the first batch, they are not rich in color, they are mostly whitish. Whereas images of the flowers which are in the second batch or batch 2, they are very rich in color. So as a result, when you try to extract the features out of these flowers which are whitish in batch 1 and which are very colorful in batch 2, the distribution of features of the flowers in batch 1 and the distribution of features of the flowers in batch 2, they are likely to be different. So as a result, I can have a situation like this. So in the first case, the flowers, we can have the feature distribution something like this, whereas non-flowers could have a distribution of features which are like this. So these are the distribution features in the non-flower category. As a result, you find that your classifier boundary will be something like this. Whereas in the second case, again, because now the flowers are more colorful, so it is quite possible that the distribution of features for the images belonging to flowers will be something like this, whereas the distribution of features of the images which do not belong to the flower category may be something like this. So as a result of that, your classification boundary will be something like this. So now you find that though your images belonging to the same category of flowers, but because of their appearance, the computed features may have different distribution. And as a result, while training, the classifier simply hops from one boundary to another boundary. In some cases, it will decide this boundary. In some cases, it will decide this boundary. So as a result, the time taken to train the classifier or the time taken to train your deep neural network becomes very large. So this can be avoided if we can somehow normalize the feature vectors so that the distribution of all the feature vectors belonging to the same class will be more or less same. And the kind of normalization that we can apply in this case is a type of normalization that we have already discussed. Say for example, for every feature or the set of feature vectors belonging to a particular batch, this is a set of feature vectors x, I can compute the mean of the feature vectors, which is mu x. I can also compute the standard deviation of the feature vectors, which is sigma x. And then I can normalize this x as x hat is equal to x minus mu x upon square root of some epsilon plus sigma x square. And this we have already discussed before, that this epsilon is a very small positive quantity. This ensures that if this sigma x somehow becomes 0, I don't have a situation of unstable division. That means I don't get a case of division by 0. So this is a sort of normalization that can be used. Now you find that this sort of normalization, what we have discussed is with respect to the input, because we are feeding the images to the input layer. This is applicable not only in the input layer, this is also applicable in the hidden layers as well. Why should it be applicable to hidden layers? So now let us try to see that why do we need normalization even in hidden layers. So to discuss about that, to see why you need normalization in the hidden layers, let us look at a typical architecture of a deep neural network. So the architecture of a deep neural network, as we have already seen, that it will be something like this, that I have a number of layers. In every layer I have a number of neurons, which is like this, right? And from every layer to every other layer I have a set of parameters or set of weights. So if this is my lth layer, this is my L minus first layer, this is L plus first layer, and so on. So from every layer, say L minus first layer, the activations are fed to the lth layer through a set of parameters or through a set of weights. So every node in the lth layer gets an weighted sum of the activations of the previous layer, and then on this weighted sum it performs another nonlinear operation, and the kind of nonlinear operation function that we are considering in this case is ReLU nonlinear function. So at the lth layer you get an activation vector, let me call it an activation vector, say AL, where it will be AL1 from the first neuron, AL2 from the second neuron, and so on. So those are the components of this activation vector. And this activation vector is fed to the next layer, that is L plus first layer, that computes the activation L plus 1, which is fed to layer say L plus 2, which computes AL plus 2, and so on. Now during training, at the final output I have some activations, say O at the final layer, say OF. So this is the final output that I get from the output layer. Okay, to make it clear, instead of O, let me use the term, say my final output will be say some F at the final layer. And during backpropagation, what you do is you compute your error at the output, and then following the gradient descent procedure in the backward pass, you pass that gradient to the layers from the output side to the input side, and while doing so, in every layer you go on updating the weight vectors or updating the parameter vectors. That is what you do. Now when you come to the updation of, or say come to this layer L only, you find that L, the layer L, gets activations from layer L minus 1, which are say activations AL minus 1. And based on the distribution of AL minus 1, you adjust these weight vectors of layer L. Now find that if AL minus 1 is steady, that means in every epoch the distribution of AL minus 1 remains the same, then learning of the layer AL will not be a problem, because the distribution of AL minus 1, which is coming from L minus first layer, that remains the same. But what happens that during this training process, this layer AL minus 1 is also updating its weights. That means the weight vectors from layer L minus 2 to layer L minus 1, that is also being updated. The weight vectors from layer L minus 1 to layer L, they are also being updated. So as a result, this AL minus 1, the distribution of this may not remain same over the epochs. So even if you are feeding the same input in the same batch, the distribution of AL minus 1, the features which are computed at AL minus 1 may be different in different epochs. So leading to the same problem of covariate shift. So even here, even in the hidden layers or the internal layers, I have to take some action so that this covariate shift can be minimized. So for minimization of this covariate shift, as we have seen before, that I have to go for normalization of these weight vectors, and in most of the cases what is tried is that you remap these vectors in such a way that the mean of all these feature vectors becomes 0 with a variance or standard deviation equal to 1. So with this introduction, that I need normalization not only at the input layer on the raw data, I also need normalization even at the hidden layer, because the features which are computed from different layers, even for the same input over different epoch or different training instances, the distribution of those feature vectors may be different, which I have to take some measure to arrest that shift of the distribution. So this is how the covariate shift, the problem of covariate shift has to be addressed. So let us see that how we can do it. So there are different ways in which this normalization can be done. One of the technique is what is known as batch normalization. You can also have what is known as layer normalization. You can have another technique known as instance normalization, or you can also have a group normalization techniques. So these are the different variants of the normalization techniques, and we'll see a bit later that the main difference is the way you compute the mean and standard deviation. So first let us discuss about what is batch normalization. So in case of batches, as we said earlier, that you are feeding the inputs in batches, right? You have the inputs from both the positive class as well as negative classes. And in every layer, so let us assume that we are now talking about some layer, say Lth layer. In Lth layer, we have, assuming that this is a convolution neural network, in Lth layer, I have a number of convolution kernels. So depending upon the number of convolution kernels, there will be different channels of features which are computed. And all these feature channels, when you concatenate together, that becomes a feature map, and this feature map is now then fed to the next layer during the forward pass. So let us assume that in a particular batch, so these are the different examples, training examples which are provided in a particular batch for training of the deep neural network. And in the nth layer, every convolution kernel forms a feature, and let us assume that the number of convolution kernels in the Lth layer that we have is 5. So as a result, I have 5 different feature components. Each of these feature components are of size, say w by h, where w is the width of the feature map and h is the height of the feature map. So finally, the feature map which goes to the next layer, L plus first layer, that becomes a tensor. This tensor have 5 channels, which is same as the number of convolution kernels that I have, okay, and the size of each of these channels depends upon how you compute the convolution, whether it is with stride or without stride, and how do you perform the pooling operation. Okay, as we said, that pooling is nothing but pooling eventually gives you a sort of dimensionality reduction or data reduction of the features that you compute. So assuming over here that a particular batch has got, say, these 4 different images, training images, I have these 4 different feature maps where every feature map has got certain number of channels and every channel has certain width and certain height. So this is the kind of feature maps that you get, which are to be fed to the layer L+1. Now what you do in case of batch normalization, in order to explain that, let me arrange the feature maps or the channels in this form. So over here in the horizontal direction, what I put is the different training examples in a given batch, say B. So these are the training examples in a given batch. And in the vertical axis, what we have put is the different channel indices. So obviously the number of such channels that you have, as we said, is same as the number of convolution kernels. And each of this channel has a size, it has an width W and height H. So that is the size of every channel, and all these channels being concatenated together gives you the feature map. Okay. So N actually gives you what is the batch size. I have N number of examples, training examples in a particular batch, and C is the number of channels, and W and H is the width and height of every channel. So let us organize our feature map something like this, and this will help us to explain how the different types of normalizations, the batch normalization, instance normalization, layer normalization, group normalization, and all that, they work. So first we are talking about the batch normalization. In case of batch normalization, what you do is you collect all the identical channels from all the training examples in the same batch and group them together. So here what you have done is, so if I put this as, say, channel number 0, this is channel 1, channel 2, channel 3, channel 4, and so on. So this is channel 0, channel 1, 2, 3, 4, and so on. You find that in this group, we have made a group of channel zeros computed from all the training examples. This is a group of the features in channel 1s from all the training examples. This is the group of features from channel 2 from all the training examples. And then when you compute the mean and standard deviation, you compute one mean for this and one standard deviation for this. Say this is mu 0 and standard deviation 0. I am putting it as subscript 0 because they are computed from the 0th channel. This may be mu 1, sigma 1, this may be mu 2, sigma 2, and so on. So these two parameters, mu and sigma, are computed from identical channels, the same channels over all the training examples. And that is how you compute the mean and sigma in in the batch normalization technique. And using these mean and sigma values, you go for normalization of the data. So let us see how this is done. So basically, when you are computing the mean of a particular channel, this is your expression, say x I c j k. So this x represents one feature element in channel C, okay, at location jk in that particular channel feature, okay, and the number of such channels or the number of training examples that we have is total n. So mu c, that is the mean of a given channel, is given by x I c j k, where I and j, I said, are the column and the row index within a single channel, okay, and j and k represents the row and column index within a given channel C, and I is the index of the number of training examples that you have. So the way you compute the mu c, mu for a particular channel, is given by this expression. In the same manner, you compute the variance, that is sigma c square over following the same indices, it becomes x I c j k minus mu c square of that, and you sum it over I, j and k, and then you normalize with n, w and h, and that becomes the variance for channel C. And using this variance, you go for normalization as we said before. So your normalized feature value x hat now becomes x minus mu c upon square root of epsilon plus sigma c square. So this is your normalized value. So as a result, if I can put it in another form also, all the channels put together can be represented as a vector. So what I do is I compute the mean vector mu b over a batch which is given by xi, I varying from sum of xi, I varying from 1 to m, and then you normalize with respect to m. So in this expression, m is the number of examples that you have within the batch, or the number of training samples within the batch. In the same manner, you compute sigma square within a batch, that is sigma b square, and then you normalize xi with respect to this mu b and this sigma b. So your normalized value becomes xi hat, which is xi minus mu b upon square root of epsilon plus sigma b square. So this is what is your normalized value. So once you do that, you find that all these normalized features, that is xi hat or the collection of xi hat, will have a mean value equal to 0, because from every x I have subtracted mu b, which is the mean vector. Okay, and then you have divided, you have normalized with respect to the standard deviation, which is sigma b. So as a result, all xi hat will have mean 0 and standard deviation 1. Now we find that there is one problem. If for every data I map it to, or I do some transformation, this normalization, so that for all type of data your mean is 0, standard deviation is 1. Then you find that the data, or this new distribution, the redistributed data, loses its class identity, because every data now have the same distribution, that is mean 0 and standard deviation 1. So which is not actually good for your classification purpose. For classification, every distribution should retain its class identity. So in order to do that, you are not only satisfied with the normalization with respect to mu and sigma, but what you need is, you need some sort of reparameterization. So this xi hat that you get, this is now reparameterized. So what you do is, from this xi hat, you map it to another data yi, where yi is gamma xi hat plus beta, where this gamma and beta, so now gamma becomes the standard deviation of this reparameterized data, and beta becomes the mean of this reparameterized data, and that is what your batch normalized output. So this batch normalized output, so this new distribution that you are generating, that has two parameters, one is gamma, other one is beta, and both this beta and gamma are trainable or tunable. So while you train your neural network for the parameter vectors or weight vectors during gradient descent procedure, at the same time you also train the neural network to tune these two new parameters, which are gamma and beta. And these two new parameters, as they will be tuned with your input data during the training process, these two parameters will retain the class identification, which will be subsequently helpful for classification of the data. So how that is done? So you put that over here. So what I need is, if I want to tune these parameters gamma and beta during our gradient descent approach following the in the back propagation learning technique, obviously I need to get the gradient of the output error with respect to this gamma and beta. And you find that, as has been shown in this mathematical derivations, the derivations are here. I am not repeating them. You can verify this, that these derivations are correct. So through these derivations, it has been shown that this reparameter or the normalization and the reparameterization that we have done, this is differentiable with respect to the parameters gamma and beta. And because it is differentiable, I can use the same gradient descent approach for tuning or for updating the gamma and beta values. So for doing that, what I need is, over here this L is the loss function. So what I need to compute is del L del gamma, which is given by this, which is del L del yi into xi hat. Take the summation over all the samples in the batch, that is I is equal to 1 to m. Similarly, del L del beta, which is the gradient of the error with respect to beta, which is nothing but del L del yi. So again, you find that you are following the chain rule of differentiation, and you take the summation for I is equal to 1 to m. So once you have this, then obviously your updation rule will be gamma gets gamma minus del L del gamma, and the new beta gets beta minus del L del beta. So it is the same gradient descent rule that can be applied in the back propagation learning stage for updation of these new parameters gamma and beta, and they will be finally tuned. And as a result, what you are doing is you are normalizing the data at every layer, whether it is the input layer or any of the hidden layers. And the purpose of this normalization is, as we have seen, that because of the covariate shift, the distribution of data from batch to batch can vary widely. And the purpose of this normalization, this batch normalization, is that it tries to make sure that even if there is a shift or covariate shift, the amount of shift will not be much. It will be within limit. And because of this, during the training process, your classifier or the classification rule that you are generating through your deep neural network, the classifier will not hop much from one classification boundary to another classification boundary. And as a result, your training process will be much faster. So in today's discussion, what we have discussed is the batch normalization technique. In the subsequent classes, we will talk about other classification techniques. And as we have already said, that the difference of other normalization techniques, and as we have already said, that the difference in this normalization techniques is basically how do you compute the mean and the standard deviation. Thank you.